Hello everyone and welcome back to Diksha Karnataka YouTube channel, and you are watching KCET 60 out of 16 physics series, where we are discussing every chapter, topics and previous year questions. Also on Sunday we are giving you a 30 questions on our WhatsApp channel. The link is given in the description. You can join our WhatsApp channel to get all the latest update that is happening in KCET 2025 exam. Also, I will be giving you the chapter notes, the notes that I am going to do in this class, so that will also be available in our WhatsApp channel. Now, let's start with today's topic, torque on a loop and magnetic moment. Let's start with all the details that we are going to study today. We will start with torque on a rectangular current loop, very important concept. Then circular current loop as magnetic dipole, another very important concept. Then moving coil galvanometer. Then galvanometer to ammeter and galvanometer to voltmeter. These will be our topic of discussion today. So let's start with torque on a rectangular current carrying current. So rectangular current carrying current is, suppose we have a loop, okay, we have a loop like this, and I want to find the torque acting on it. What is the meaning of torque? There should be two equal and opposite forces, but they are not acting on the same object, they are acting on a separated by a distance. So as we have already calculated that there is a force between two parallel wires. Now here we have already have an external magnetic field, north to south, an external magnetic field is present. Now what will happen in this case? The torque is given by I times A times B. Okay, what are all these terms? I is current on any one of the wire, any suppose if I current is flowing here, then you can say this is the current I, right? What is A? A is the surface area. A is the surface area of the loop, okay, and B is the already present magnetic field. B is the already present magnetic field which is between north and south. That is the formula for the torque. Now torque is a vector quantity, so we can write torque as I times, now current is not a vector quantity, surface area is a vector quantity. We learned about surface as a vector quantity in Gauss's law, remember that. So surface area we can consider this as a vector, and B is obviously a vector quantity. It is from north pole to south pole for a magnet. So we can write the torque as a vector quantity like this. Now the magnetic moment of a single loop is defined as, magnetic moment is defined as I times A. This is very important. Okay, we have not discussed anything about magnetic moment, magnetic dipole yet. So you might be wondering why I am defining this, because there is a similarity. Okay, for n number of turns the magnetic moment is given by NIA. You should remember that N is total number of turns. So here it is only one turn. So now if I have multiple turns here, most of the cases we will actually have multiple turns. So suppose you have n number of turns, then magnetic dipole moment is given by NIA, National Investigative Agency. Okay, now in this case we can write torque is equals to M times B. Now if you remember, the torque for electric field, torque on a electric field, electric dipole was given by, torque was given by P cross E, right? Therefore this is basically similar to that of an electric field. Instead of electric field we have magnetic dipole moment and we have magnetic field. So that's why we have defined this as magnetic dipole moment. Basically it started from the symmetry. Later on when we deep dive into the theory part of magnetic dipole, then it will be clear. Okay, now let us solve one small problem. A circular current loop of magnetic moment M is in an arbitrary orientation in an external uniform magnetic field. The work done to rotate the loop by 30 degree about an axis perpendicular to its plane. Okay, so circular loop, even though we have learned that formula for rectangular loop, that same formula is applicable for circular loop as well. Okay, now they have said that it is a circular current carrying loop of magnetic moment M. So the magnetic moment is given capital M, okay, in an arbitrary orientation in an external uniform magnetic field. So it is an arbitrary orientation. Okay, so does not matter how it is oriented, some arbitrary, I am taking some arbitrary orientation. Now they are saying that what will happen if I rotate this loop along its own axis. Okay, now if you rotate this loop along its own axis, is it anything changing? So you have to think, suppose this is the loop, okay, and some arbitrary direction was the magnetic field. Now if you rotate this loop, okay, in any direction, either clockwise or anti-clockwise, symmetry wise nothing is changing. Okay, so symmetry wise nothing is changing. If you have rotated it like this, okay, like this axis, okay, diametrical axis, then something would have been changed. But if you are rotating it along this axis, that is axis outside the plane, then nothing is changing. So we can say that in this case the work done should be 0, because it does not matter how you are rotating, how much angle you are rotating, because nothing is changing symmetry wise. So we can say that work done must be 0. Simple question. Okay, this is not very technical, not very critical question, but you have to understand the physics behind it. If you understand the physics behind it, then you can answer the question. Now circular current loop as a dipole. Now what we are going to do is we will understand the circular current loop. We already find the magnetic field due to a circular current loop at some point P. Okay, the radius was given by r, this distance was given by x. Then this was the formula, if you remember. Now if this distance x is very greater than the radius of the loop, okay, then we can write this formula as mu naught I r square by 2x cube, right? So what we have to do, we have to put this value 0, because x is very large than r. If you remember dipole approximation, right? If you remember, in case of dipole approximation, we have only for terms in denominator was goes to 0, because that was being added to the distance, right? R plus a. So in that case we have ignored the a square term, because r square term was supposed to be greater than that of a square. Similar to that, we have ignored this r square term here, because r is very small compared to the distance x. So we can simplify this as mu naught times I r square divided by 2x cube. Now let us multiply pi in the numerator as well as denominator. So this r square is basically area, right? This is the area of this circle or the loop, right? So pi r square is the area. So mu naught Ia divided by 2 pi x cube, or Ia. What is Ia? I told you what is Ia. Ia is basically the magnetic dipole moment for a single loop. For multiple loops, if there are n number of turns, then we write it as NIA, National Investigative Agency, right? So we can replace Ia using m, and then we can rewrite this equation as mu naught by 4 pi 2m by x cube. If you remember the formula for dipole moment of electric field on the axis of a dipole, a magnetic dipole, or on the perpendicular bisector of a dipole, we got similar formula, right? We got 2p by x r cube one case and 2p p by r cube in another case, right? Similar to that, we are getting formula 2m by x cube. So that is the magnetic field on the axis. Now what is the direction? So because we are considering current loop, there has to be some north pole and south pole. So basically when we are observing from side where the current is moving in this direction, okay, then we can say this is a north pole. Okay, if you see from one side, current will appear in this direction, from other side the current will appear in the opposite direction. So when you are seeing there is a dipole, means it is behaving like a magnet. Okay, dipole means basically a magnet. Okay, simple terms. So if it is moving in this direction, okay, then it is a south pole. If it is moving in the opposite direction, then it is a north pole. Okay, so if it is moving in the clockwise direction, south pole. If it is moving in the anti-clockwise direction, then it is a north pole. Okay, so and the formula for magnetic field is given by 2m by x cube. Okay, mu naught by 4 pi is common, as I said at the beginning. Now let us look into the homework problem. A long cylindrical wire of radius r carries a uniform current I flowing through it. The variation of magnetic field with distance from the axis of the wire is as shown. So yesterday I discussed this problem while discussing the theory. So from there the correct option is option A. If you have not yet seen yesterday's video, go and please check yesterday's video. There I have said why this is correct and why these are not correct. Okay. So the simple question, only theory based question. Now the second question, a straight current carrying conductor is kept along the axis of a circular loop carrying current. The force exerted by the loop on the straight conductor is in the plane of the loop towards the center, 0, perpendicular to the plane of the loop, in the plane of the loop, away from the center. So what is the meaning of that? We have a loop, we have a conductor. Okay. So basically it says that a loop is kept along the axis of a straight conductor is kept along the axis of the loop, right? So they are saying that what is the force. Now if the current is going in the same direction, okay, then they will repel, but if this is going in the opposite direction, then it will attract. Now from one side it will be repelled in this direction, from other side it will be attracted, right? So here we have a loop and a straight wire passing through the loop. Okay. So the straight wire passing through the loop. Now if you see, the current is moving in this direction, and in case of the loop, current is moving in this direction. Now what formula that we have learned, in that case they are on the same plane, current is passing in the same plane, but in this case they are not on the same plane. One is along this plane, another one is this plane, so they will not interact with each other because the magnetic field lines are not crossing and they don't have any component. This loop will not have any component in the direction of the loop, so we can say that magnetic field, these two magnetic fields are not interacting, so the force will be 0. Okay. So be careful while answering 0, even though 99% of the cases 0 may not be an answer. For JEE, for KCET, 10 to 20% cases 0 can be a correct answer. Be careful about that. For JEE, if you are writing JEE NEET exam or JEE advanced exam, 0 is the least possible answer. Okay, 0 is the least possible answer, but in KCET 0, it has been observed that 10 to 20% cases 0 can be a correct answer. Okay. Now moving coil galvanometer. So we have learned that when we are considering a single loop, it behaves as a magnet or it creates a magnetic field. Now when we are keeping that loop inside a magnetic field, okay, it also experiences a torque, right? So that also we have discussed in our first part, that rectangular loop, it experiences a force in IAB, right? So in IAB, that is the force acting on a loop. Now if we consider a loop like this, okay, this is a circle where they have made the loop like this, okay, and if it is kept inside a magnetic field, that is we have kept one north pole, one south pole, then it can be treated as a galvanometer. What is the meaning of that? Whenever a current is passing through this coil, it will detect that current and it will give you some deflection. Okay, so the galvanometer is a device which can detect the flow of charge. It directly cannot measure current, it directly cannot measure potential, but it can measure the flow of charge. Basically it can measure whether there is a current is passing through the galvanometer or not. Whenever there is a current passing through the galvanometer, it will give you a deflection. Now that deflection, angle of deflection is given by G times I. Here G is a constant based on the galvanometer. Okay, so angle of deflection is directly proportional to current. If the current is more, the angle will be more. If current is less, galvanometer deflection will be less. Okay, now G is basically given by NAB by K. K is another constant. Okay, and NAB basically number of turns, area of the loop, B is the magnetic field. These are constant for a given galvanometer. Okay, for a given galvanometer, if the galvanometer is already there, you cannot change the number of loop, you cannot change the magnetic field that is already there, okay, and you cannot change the area. So everything is fixed in this case, so that's why it is called galvanometer constant. Generally, we take this as galvanometer constant, and we most of the cases we are not bothered about this value, but some cases we actually need to learn about that. So let us understand this question. The torque acting on a magnetic dipole placed in an uniform magnetic field is 0 when the angle between the dipole axis and the magnetic field is. So this is related to dipole, not directly related to galvanometer. A torque acting on a magnetic dipole placed in an uniform magnetic field is 0. So torque is, what is the value of torque? M cross B. Remember that it is similar to P cross E. Okay, instead of P it is M, instead of E it is B. Okay, now if we only consider the scalar value, it is MB sin theta, obviously. Okay, now it is mentioned that the torque acting on the dipole is 0. Torque is 0. Okay, so the magnetic field, the uniform magnetic field, when the angle between the dipole axis and the magnetic field. So what is the M cannot be 0, B cannot be 0. So only thing that can be 0 is sin theta. Okay, so if the angle between them is theta equals to 0 degrees, then only it is possible that the force is 0, because sin theta is 0 only when theta is 0. So correct option is option D. This is also a previous KCET question. Now let us convert a galvanometer into an ammeter. How can we convert? First of all, a ammeter is a device which should have 0 resistance. In practical ammeters, the resistance is kept as low as possible. So ammeter is basically a device which measures current in a device. Okay, ammeter is a device which measures the current in a device. So to measure the current, it has to have a low resistance, right? We have learned that in our Ohm's law chapter, V is equal to IR. So I should be V by R. Now suppose V is constant, given circuit V is constant. Now this was supposed to be the current, right? Now you are adding an ammeter to measure this current. So ammeter should have some internal resistance. So what will be the current now? The current should be R plus R. So when you added this ammeter, the current automatically drops from the original value. You are only applying the ammeter only for a second to measure the current. Later on you want to remove the ammeter, because if you see our day-to-day circuit, do you see ammeter fixed everywhere? No, right? Ammeter is only when it is required, when your device is broken down, repairman comes, he is to test how much current is flowing, then only he uses the ammeter to measure the current, and as soon as it is done, he will close the ammeter, right? So ammeter should be something which ideally has 0 resistance, so that it does not affect the actual flow of current. But in practicality it is not possible to form something which has 0 resistance, right? So what we want this resistance to be as low as possible, so that the effect of the original resistance R is still the priority, right? Even if it is decreased, maybe it is decreased by 1% or 2%, that we can ignore, right? So we have to keep the resistance of the ammeter as low as possible, because it is measuring the current. Now to convert a galvanometer into ammeter, we need to connect a shunt resistance. What is the meaning of shunt resistance? Shunt means small value resistance, okay, and it is connected in parallel. Okay, shunt means a small value resistance is connected in parallel, that is called shunt. So shunt is when we are connected the small value resistance, okay, most of the current coming here, that will pass through the small value resistance, and very small amount of current will actually pass through the galvanometer, okay. And the current sensitivity of the galvanometer is given by phi by I. Phi by I is NAB by K. Very important relation. Sometimes they will ask you what is the current sensitivity, what is the voltage sensitivity. Now you should remember that if we increase the number of turns, its current sensitivity increases, okay. So current sensitivity basically dependent on N. So if we want to construct a galvanometer having very high current sensitivity, that is, current sensitivity means suppose current changes from 1 ampere to 1.1 ampere. if the device can detect that, then it is very sensitive. But if not 1 ampere, say 1 milliampere to 1.1 milliampere, and if the device is able to measure that 0.1 milliampere difference, then it is said to be highly sensitive. That is an example, right? Now if suppose the current is changing from 1 ampere to 2 ampere, then only the device is able to measure it. Then it is not very good current sensitive device. Okay, so the current sensitivity is something which is how a small current change is detectable, then that device is called highly sensitive. Similar to that, when the changes is not significant, changes is big, but still it is not able to detect it, then that device is not highly sensitive, right? So current sensitivity depends on 3 things. N, A, B, K is basically a constant. So number of turns you can increase to increase the sensitivity, area you can increase to increase the sensitivity, but if you increase the area, your ammeter size will be very big. So that is also not possible. Similar to that of B, if you can increase a very high powerful magnet, then your device will be highly sensitive. If you cannot use that, then your device will not be that highly sensitive, right? So these are the few things that you need to consider. Number of turns is the easiest way to increase the current sensitivity. Okay. Now if suppose one more thing, current coming in the galvanometer, say I, total current coming in the galvanometer is I. Okay, out of that, current passing through this is Ig, and current passing through the shunt is Is. Now you should remember that you need to remember few formulas, that I should be equals to Ig plus Is. Okay, also Ig should be equals to I times S divided by G plus S. G is the resistance of the galvanometer, or Rg. Okay, they have mentioned Rg, so I will use Rg. Okay, so this is the current through the galvanometer, and current through the shunt is given by I times G divided by Rg plus S. So if you see, when we are finding the current through the galvanometer, we are using shunt resistance. Okay, shunt resistance is given by small s, right? So we can find Ig and Is from this value, from this formula, right? So this is a very important formula. Sometimes problem comes from this formula as well. Okay, we'll solve few numericals. Now galvanometer is a device which is used to measure the voltage. Now voltage means what? Suppose I have a circuit, I want to connect the galvanometer, connect the voltmeter in parallel. Now you should remember one more thing, is that voltmeter is connected parallel, whereas ammeter is connected in series. That is also one more important point to remember. Okay, so voltmeter is connected like this. Now what you want to draw as minimum current as possible from the circuit to measure the voltage across this resistance, because if you draw maximum current into the voltmeter, then there will be very less current passing through the resistance. In that case, you will not be able to measure the actual voltage that you are supposed to measure, right? So for that, ideal voltmeter should have infinite resistance. So if the resistance is infinite, it will draw zero current and it will give you the correct value. But if it is drawing zero current, practically it is not possible for it to work. So in that case, what should we do? We should keep the resistance very high. Okay, so we need to keep the resistance of the voltmeter as high as possible. Okay, to convert a galvanometer into a voltmeter, we need to connect a high value resistance in series to the galvanometer. Okay, this is the very high value resistance. It does not have any name like in case of ammeter, and the voltage sensitivity is given by NAB divided by RK, where R is the resistance of the galvanometer. Right? Now you should remember that in our previous case I said, if we increase the number of turns in case of ammeter, you can increase the sensitivity of the ammeter. But what will happen if we increase the N? Okay, what will happen for voltage sensitivity? So voltage sensitivity, basically you cannot always change using number of turns. Why? Because we know that number of turns means you are increasing the length, right? You are increasing the length, and resistance is basically proportional to length. So more number of turns means resistance will be higher. Okay, in fact, N by R can be considered as a constant. N by R for a given galvanometer can be considered as a constant. Okay, and it does not matter how many turns you add. Even if you increase the number of turns, R is also increasing proportionally. So suppose initially you had 100 turns, okay, you measured some voltage sensitivity. You thought, okay, I have done the same thing for ammeter. To if I make it 200 turns, it will its sensitivity should increase. But what will happen in that case? If you double the number of turns, okay, that is number of turns will be doubled. Similarly, the resistance will also be doubled, because resistance is directly proportional to length. You are also increasing number of turns, means you are increasing the length also by double. So resistance will be increased. So N by R ratio will remain constant. So you cannot change the voltage sensitivity by increasing the number of turns, but current sensitivity can be increased, right? Now in this case, whatever current is passing through this, same current is passing through both of them. So current is passing through I, current is passing through this, current is passing through this. So in this case, no such current formula is required. Okay. Now a very important question. A galvanometer of resistance 50 ohm is connected to a battery of 3 volt along with a resistance of 2950 ohm in series. A full deflection of 30 deviation is obtained in the galvanometer. In order to reduce this deflection to 20 deviation, the resistance in series should be. So first of all, let us understand what is the meaning of this full scale deflection. So full scale deflection means a galvanometer or any other device, okay, generally has a scaling, right? For example, if you take your scale, okay, in your geometry box, so it can measure from 0 centimeter to 15 centimeter. So full scale deflection means that 15 centimeter. Similar to that, the galvanometer you may have done in your laboratory, may have seen that in your laboratory. Okay, they also have a scale. Circular scale generally starts from 0, okay, and it goes to some maximum value, say 30. In this case, 30. Okay, in this case, the full scale deflection is given as 30. So there is 1, 2, 3. So there are different scale element is given in this galvanometer, and total number of scale is 30. And when the galvanometer needle rotates from starting from here till it rotates the maximum possible angle, then it is called full scale deflection. Full scale deflection means from 0 to maximum. Okay, now we can change this deflection by controlling the current. Okay, so initially what is the full scale deflection? When 50 ohm resistance is connected in 3 volt battery and the internal resistance of the galvanometer is 2950. So what is the diagram? First let us draw the circuit diagram. So G with internal resistance 2950 and external resistance 50 ohm. Okay, it is connected to a battery of 3 volt. So what is the equivalent resistance? To find the equivalent resistance, these two are connected in series or parallel? Series, right? So these two are connected in series. So what we have to do? We have to just simply add them. So 2950, the values are given such that if you add them, you will get a very good value. So 2950 plus 50 is 3000, right? So 3000 is the new equivalent resistance. Now what is the current in the circuit? Current in the circuit is 3 volt divided by 3000, that is 10 to the power of minus 3 ampere. Okay, you solve it, 1 by 1000. 1 by 1000 means 10 to the power of minus 3 ampere. So this is the current. Now for this much current, it is showing 30 deflection. So for this much current, it is showing 30 deflection. So what we have to do? We have to increase that resistance. We have to increase that 2950 resistance, so that the same current, for same current, the deflection is now 20. The deflection is now 20. So for what we have to do, how can we reduce the current, because the voltage source is fixed, right? So what we have to do, we have to reduce the current, right? How much we have to reduce? The new current, say I dash, should be equals to 10 to the power of minus 3. What is the new division that we want? What was the old division that was there? So we need to reduce the current by 10 to the power of minus 3 ampere. This should be our current. So how much should be the resistance? Voltage is fixed. So V is equal to IR. Okay, V is 3 equals to 2 by 3 times 10 to the power of minus 3 times R, or R equals to 3 times 3 times 10 to the power of 3 divided by 2. So this 10 to the power of minus 3 coming in this side becomes 10 to the power of 3. These two will go in division and these two will come up. So it will be 9,000. 3 times 3 is 9. 10 to the power 3 is 1000. So 9,000 divided by 2. So it will be 4,500. Okay, 4,500 or 4,500. So this should be the total resistance. So this should be the total resistance, right? Now out of that, external resistance was how much? External resistance was 50 ohm. So the external resistance that we need to add should be 4,500 minus 50, that should be 4450. So 4450 ohm is the answer. So we have to check, and answer is 4450. Okay. Now we have reached end of the lecture. So please note your homework for today. This is a very simple question. Similar to that we have solved already. Try to answer this question and mention the answer in the comment below. While mentioning the answer, please mention homework number 1, answer option A, option B, option C, whatever you think, okay, whatever you have calculated. So while mentioning, please mention homework number, otherwise it is very difficult for me to understand which question you are trying to answer and answering in the question. Okay. Next is homework 2. Pause the video, read the question, solve it, mention homework 2 and answer the option, right? As you know, we are uploading each and every video that we are doing on our channel in this playlist. So follow our channel, follow this playlist, so that whenever we are adding any video into the playlist, you get a instant update, and whenever you want, you can come back here and you can check all the videos available in this playlist, and you can study at your own pace. Okay, but you should make a plan and continue study. Also join our WhatsApp channel to get all the lecture notes, to get tomorrow's KPL question paper. Tomorrow we are obviously conducting KPL as usual. Tomorrow is match number 3, so don't forget to download your question paper from this WhatsApp channel. Also it will be shared in our community post in our YouTube channel. So don't forget to download the question paper, answer those questions and check your answers in the evening when I am doing the discussion. Okay, so thank you for watching this video. If you have not yet subscribed, don't forget to subscribe to our channel.